Next speaker to come on the stage, Professor Stephen DenBaars from UC Santa Barbara. And Stephen will be telling us about developments in high efficiency, ultra small micro LEDs based on III-Nitrides. So the stage is yours, Steve. You have 15 minutes. 5 minutes in, I will give you a heads up. 2 minutes before the end, I will also, sorry, 10 minutes in, I will give you a heads up. 2 minutes before the end, I will
Okay.
also give you another heads up.
Just a sound and visual check. Can you see the full screen and hear me okay?
I can hear you well, and I can see you, and I can see the slides. All good.
All good. Okay. New platform. Okay, great. So today I'm Oregon Academic Research Institute at the University of California, Santa Barbara, and we're one of the largest academic research institutes looking at micro-LEDs with over 4 faculty members and over 25 PhD students and about 15 undergraduates. So the topics we're really addressing are some of the key material science and device problems in the micro-LED arena, particularly the efficiency drop as you decrease the size of the micro LED from 40 microns or so for mini LEDs all the way to 10 microns. And then I'll show you some recent data where we have now 1 micron RGB micro LEDs working. Also, we do research in the indium gallium boron nitride materials for green and red. And there we're trying to shift the wavelength of the blue basically based nitride LEDs into the green and red to get full coverage in one material system. And I'll tell you about some motivations why we want to do that. So the key reason why we focus most of our research to now below 10 microns is that augmented reality really needs sizes below 4 microns, is what we hear from some of our industrial members, to really hit some of the 5,000 pixel per inch kind of requirements you need for AR and mixed reality. Some of the other markets that you're all looking at, smartphones and even TVs, if we can get high efficiency reproducible LEDs below 10 microns, that will actually help you a lot with the cost requirements as well, given that you can put more, use more epi and decrease that cost. So there's been a lot of talk over the last 5 years about what materials we should use. So I think first generation micro LEDs are going to use aluminum gallium indium phosphide for the red and indium gallium nitride for the green and blue. Of course, there's also other approaches for using blue with quantum dots and color conversion, but most of those are sizes above 4 microns or so. So I'm tending to focus more on the smaller side. We were told by several of our industrial members that they would like us also to work on indium gallium nitride in the red. And so we've pushed that over the last few years. The efficiency here is shown on the left, where we're now 50% in the blue and over 30 to 40% in the green. We pushed the red now to where we're at 6% at small LED sizes in the red. And that is now getting competitive with the aluminum gallium indium phosphide line, which is shown here, because the problem with aluminum gallium indium phosphide is as you drop to sizes below 50 microns, as you'll see here in these two reports from LG and also from Royo, is that once you decrease the size in the red, the efficiencies tank even faster than they do in the nitrides. This one shows you efficiency dropping over 5-fold as you go from 262 microns square to 32 microns square. And this is some work from LG where they show as they went from 350 down to 15 by 15 microns, that basically they also saw a 3-fold drop in efficiency. And so the indium gallium nitride material system, as I'll show you, has a much less severe efficiency drop. So when we started this research, initially efficiency drops looked like this, where we could get about 25% for 40 to 60 micron sizes. But as you got to sizes below 40, the efficiency would drop pretty quickly. And this data only went to 10 microns at that time. And what we elucidated is in our current UCSB design for micro-LEDs is that conventional micro-LEDs use indium tin oxide here for the top electrode. And basically, when you etch this mesa here down to the end contact, you were getting sidewall damage, which was causing non-radiative recombination. So as opposed to larger LEDs, which you don't use atomic layer deposition, we developed an atomic layer deposition coating here of SiO2 around the mesa to help reduce the leakage current and also increase the efficiency, as we'll see for our micro LED.